one.
Yeah.
He meant one bottle.
All right, let's
There we
see. Okay, now let me see if I can't share the agenda. Let's see.
Meeting is now streaming live on YouTube. There we go.
Yeah, you just say you got it on there. That's why just
Okay.
press you got it, and that'll move you forward. 'Cause if you didn't want to be recorded, you would leave. That's all.
Who is this guy named John O'Brien? Doesn't look like I've seen him in quite some time.
Yeah.
Yeah, he's
It's an imposter.
He looks good.
We know
Looks
that's
good.
not John O'Brien. That's not what John O'Brien looks like.
We're masking again, and the masks don't fit very well over the beard, so I had to get rid of the beard.
Looks like you got rid of the hair too.
Yeah, found a nice barber. Found a barber I really liked today. Took on the fourth try. The first three barber shops I tried, they weren't vaccinated. So I just turned around and walked out.
Okay, are you guys, what are you guys seeing on the screen? I
Seeing the
can't
general
figure out.
meeting.
We're
I'm just
actually
seeing
seeing
your
your
window.
workspace.
Pardon?
Slide
Yeah,
one.
it hasn't done the slideshow yet.
Yeah,
Okay,
you're still on slide one, Spencer.
all right, hang on, let me try again.
Okay, ban those drugs.
That's you. How are you?
Hey, Daryl.
Yep.
I see Evan made it. Hey, Evan.
Hi, Annie.
So,
Hi there.
John, I had gotten up to the full beard again this morning, and I went to do a trim, and I was a little too tired. So I got a big stripe, right? I said, okay, never mind. Back to the goatee.
Okay, are you guys able to see this now?
No,
I can
We're
see
seeing
you.
Jeez,
Seeing the whole gallery of people.
okay. Hang on, let me just, darn it. All right, well, I think we'll just probably have to, all right, let me give me another 5 seconds, and if I can't get it, we'll just go without it.
you'll just have to read the agenda to us.
Yeah,
Oh, that'd be something. I could do it by announcer's voice.
You got the right mic for it.
There you go. Welcome to the Los Angeles Astronomical Society.
You need a spit screen for that.
I didn't buy one because it's just me. They make a big deal out of it, but yeah, when I'm recording, it's not a big deal.
Well, and if you're running it through a DS-er anyway, you don't need the screen.
Yeah. Don't
all right, now are you able to see anything?
See.
Let's see.
Yeah,
There you
so
go.
There we go.
Yay.
getting there.
You got it. You got
Okay,
it.
all right, I'm not gonna try to get the full screen mode at this point.
That's okay. You're good.
Okay,
Okay, well, we'll go ahead and get started with the meeting. Of course, we're recording this meeting. Also, use the chat feature for questions and comments throughout the presentation. And if it's up, it'll be up to Evan whether or not he will take questions as the presentation is going, or if he just wants to, if we're going to mute everybody during his presentation. Okay, the second item is we want to make sure that everybody signs up for the door prizes. Very, very important for the door prizes. So,
I won
and
the last
Spencer will give the link before. We'll give the link very shortly here, and then we will get another link right before we draw the door prizes. Okay. Okay, the announcements we need to make is the Garvey Ranch Observatory is closed until for public events until after Labor Day weekend. Mount Wilson, we will not have public star parties at Mount Wilson, at least until into September, maybe October. I still have to coordinate that with Mount Wilson, Davidson Dayos and Mount Wilson, but looks like we're probably not going to have any public star parties up at Mount Wilson. And Garvey Ranch, we will not have any public events, anything to the public planned at Garvey Ranch. I think the only thing we'll be doing at the Garvey Ranch is continuing the club. Some of the club members will be continuing cleaning up the operation at Garvey Ranch. Okay, how many new members do we happen to have tonight? Any new members?
Claude, but he was here for the last one.
I'm a new member.
Marcus Rich?
Yep. I am a new member.
Okay, can you tell us a little bit about yourself and why you decided to join this madhouse here?
Well, I'm from LA, and I'm in school actually for astronomy at Arizona State University. I've been watching videos and reading books for the past 15 years, and I was a little afraid to go back to school because of the math, but a couple of years ago, I said, you know what? I have this crazy passion. I'm just going to do it. Now I've been there for about a year and a half, and I'm loving it, and I just love everything astronomy. I mean, I read a lot of books. Lawrence Krauss, I'm reading deGrasse Tyson, I'm reading Brian Greene's book, and I just love the cosmos. So I said, you know what? From LA, let me see if I can join you guys and be a part of this.
Okay, fantastic. Glad to have you a part of the club.
Thank you.
Anybody else, new members?
Teresa and I are new members as well.
Oh, Clyde, okay. Clyde?
What was that?
Would you like to make a reason why we kind of suspect the reason why you joined the club, because you were a speaker at one time?
Well, I recently retired from the Big Bear Solar Observatory, relocated to here in Tehachapi. So we both Teresa and I were deeply involved with the Big Bear Valley Astronomical Society. Teresa being president, me being vice president.
Forever.
For life. But now that we have relocated, we were looking for a reasonable club to become affiliated with. And John here somewhat recommended that we check out LAAS, which seems to somewhat act in the capacity of somewhat of an umbrella organization for Southern California. So decided to add this to the long list of organizations we have belonged to in the past. Quick bio, I retired from, I was with the National Solar Observatory for 26 years, then moved to Big Bear. Teresa, you want to nutshell your background?
I worked for the MIPS group at Stewart Observatory at the University of Arizona, which is the multiband imaging photometer for the Spitzer Space Telescope. And then I worked up at Kitt Peak, also on the McMaster Solar Telescope as the telescope tech for 7-ish years. And then I tried doing some technical writing for a couple of years. I was actually pretty good at it, but I found that I didn't really like doing it that much. And so I joined then with the Large Binocular Telescope Interferometry group at Stewart Observatory again. And both of us have been active amateurs for our entire lives, I think, maybe college on.
College on, yeah.
College on, and so we were very active with the TAAA in Tucson also.
Before that, Sonoma County Astronomical.
Before that, Sonoma County Astronomical, yep. While we were in college.
Oh, yeah.
Where are you guys located?
Tehachapi.
Okay, cool.
Okay, sounds good. Welcome to the club. I've seen you before. You made a talk at our club a couple of years ago, almost 2 years ago or so. Appreciate that.
Very memorable, I might say, too.
Okay, any other new members? Okay, it does not look like we have any other new members online. Okay, would like to go to the committee reports. First, we'll start out with the Ford Committee. Joe Phipps, you want to make a little bit of a statement on Ford?
Well, there hasn't been much activity at Ford. We've been up there a couple times. Conditions were pretty good, but not a lot of club activity has happened up there since the last meeting.
Yeah, I'm probably not going to do anything till Ford for a little bit of time because next new moon cycle we'll be out of town, right, Joe?
Yep, we'll be out of Joshua Tree.
Yeah, we'll be out of Joshua Tree. Okay, next one, the Lockwood Committee, John O'Brien.
We had about a dozen people brave the smoke Saturday for a dark sky night. I didn't stay because it was actually burning my eyes, but the guys that braved it said it cleared off about 10 o'clock, and it actually turned out to be a pretty good night. We had several new members up there. I think we had at least 6 new members up there for the first time. Maybe 7. I get lost count. And so that was. I hope they didn't get discouraged by the smoke and come back next time. Come back next month. Who knows how long these fires are going to last, though. So, but
Okay.
the hatch should be cleared off pretty good today, smoke wise. So hopefully, I think the smoke's blowing back towards the east again now.
Okay, yeah, it just depends on the prevailing wind patterns. Okay, next committee report, Scouting Committee, Greg Thompson. Greg, are you there?
I haven't seen Greg on.
He's
I
here.
thought I saw him on.
Oh,
Hello, can you see me?
Sure.
Okay. Thank you, Curtis. A quick report. As general membership should be aware, we had our Astronomy Merit Badge event in June. That was online. Our July event was scheduled to be in person, and we went forward with that under, the COVID regulations at the time. And that was quite successful. And many thanks to the club members that helped prepare and get ready out at Garvey initially, and then helped out with the presentations and sharing telescopes. A number of people showed up and did quite a lot, and that was a successful event, despite everyone having to wear masks everywhere. Our August event is coming up next Wednesday, and due to the ongoing COVID situation and the recommendation of the board, we're going to convert that one to virtual or online again. So I think we've got about 20 scouts that should be joining that a week from this Wednesday. And I need a couple of volunteers that maybe could share astrophotography live. So I'll be sending a note out about that, and I'll type my email in the chat here in just a second if anyone might be interested in how they could contribute to that online event a week from Wednesday. So that'll end our season with the Astronomy Merit Badge. Was there a question?
Yeah, when you said live just now, do you mean live capture as in sharp cap, or just being able to see a screen whilst 5-minute images are being taken?
So I consider live stacking to be quote unquote live. That's absolutely, because basically what you want the scouts to see on the screen is what you're doing at that very moment in time. And so what you would do is zoom into the meeting from your laptop and then share, assuming that your control software is on the same laptop, show whatever you're seeing at the same time, and then share what you're doing and what they're looking at as a kind of live event, although it is virtual. So I'll get some information out about that. We ended up our program at 2 summer camps where I was contributing to the overnight star parties up at Lake Arrowhead, and we'll probably continue that connection going into the future. And as we wrap up this summer, we'll start looking forward to next year when maybe we can get back to live events at Garvey, where the scouts can come out and interact and look through the telescopes, which I think is much better. Although we do a pretty good job virtually. So anyway, thank you for all the support from the club. All the scouts got the little planispheres that they could use to understand how the night sky rotates around and find things that the club has generously provided for those youth outreach events. And thanks a lot. Stay in touch. And I'll put my email in the chat. If you have any questions, follow it up. Maybe you could participate, whatever you're interested in, we could always use the help. So thanks a lot.
Hey, Greg, are you trying to hypnotize us all?
Yes,
Greg,
you will.
Greg,
you will.
You want to readjust your camera because we're looking at your ceiling fan.
Spencer's the only one that's going to bother.
Sorry about that. That was my I use audio on my cell phone because it works better. So yeah, with the camera, the phone was pointed straight up at the ceiling. Sorry guys, that's a virtual faux pas there.
Thanks a lot, Greg. We do appreciate your effort on the scouting committee. Do appreciate it. You're a fantastic asset to the board. Okay, Daryl, would you like to talk about the events at Mount Wilson as far as the 60 inches is concerned?
Yeah, we have one coming up next Saturday, which is full on the 14th. And then we have one for each of the next months in September, October, and November, which all have openings. Any of you are interested in 60-inch nights, contact me at Mount Wilson Coordinator at laas.org, and I'll tell you about it. I was up there on Saturday with a hyper ticket night, which is a really nice event that Mount Wilson puts on. You buy a ticket for the night. It's a half night, but you split the half night between the 60-inch and the 100-inch telescopes. So you have two groups. I think we had 36 people, maybe two groups of 18. We take 18 into each telescope dome, and halfway through the night, we all go out and swap groups in the parking lot and take the people from the 100-inch to the 60 and the 60 go to the 100. I think they really appreciate being able to see out of both telescopes in the same night. So that's an event that Mount Wilson puts on. It's not ours, but something to look for in the future if they have those. It seems like a really great night. You get to compare telescopes on the same night. Other than that, they've gone well so far. The two events we've had so far are good. I'm looking forward to Saturday. Geo is going to be the session director on Saturday, and I'm going to be the operator. So that's on the 14th.
Okay.
Because we're not having any, public star parties to go along with those, it will just be the rest of the 60-inch nights are the only other events at Mount Wilson. Other than I think they may have one more concert. I didn't look at their site, but Mount Wilson is also doing concerts in the 100-inch dome. Is Tim Thompson here? Do we have one more of those, Tim? Or is he not here tonight? I don't see him.
I don't see him.
Yeah.
Okay. All right, that's all that's going on up there. Still having a great time. We're doing all the Mount Wilson staff are vaccinated, and we are mandatory masking with any group that are up there. So I am requiring proof of COVID for the events, and we probably will be masked as well. I'm not certain about I'm not mandatory on masking so far, but probably everyone will want to anyway. So that's it for now.
Okay, thanks a lot, Daryl. Looks like at least some activities are going on.
Sorry, I wasn't even on screen for all that. Okay.
Oh, that's okay. We heard your voice. We know who you are. Okay, I think that's all we need to do on the committees for tonight.
Curtis, what happened to your video?
On to,
you're all blurry. Yeah, you're all blurry.
Me?
Yeah.
Am I blurry?
Yeah, you got fogged up or something.
You're almost all whited out.
You're frozen. Now you're unfrozen.
That's good.
Okay.
Good. You're okay now. It was weird.
Okay, there's Mark Schaefer back. Mark, did you renew your membership? Mark Schaefer.
I'll have to look into that.
Okay, Spencer, send him another renewal package because I was supposed to get back with you and I forgot to get back to you. So Spencer, send him another renewal package, okay?
Okay.
Okay, then I think it's time to go on to our guest speaker, and also Spencer, can you put the door prize registration on the screen?
Sure, yeah. I've already,
you haven't done so already?
It's in the chat. If you just check
Okay, I'll look for it.
And,
and
during the talk, I'll repost it a couple of times because those who joined late will not see the earlier chats.
And we always make an announcement before we draw the door prizes.
Yeah.
Yep.
Okay, go ahead, Spencer. It's yours.
So this is Evan. This is a great title, Evan. How to drive a rover on Mars and other useful skills for an itinerant space traveler. So the abstract is that, so Evan is a mechanical engineer at NASA's JPL. He splits his time between operating the Mars rover Curiosity and designing architectural components for the Sphere X space telescope. Previously, he's contributed to spacecraft design and technologies ranging from a shoebox-sized small sat to 100-foot diameter deployable system. In addition to his day job, Evan is a telescope operator at the Griffith Observatory and publishes Explore and Observe, an online newsletter covering the latest in modern day exploration of Earth and space. So Evan is going to talk to us about Mars rovers. They've been the hallmark of planetary exploration for 25 years. And all 5 of them have been built by JPL to safely operate long duration missions and maximize science output. JPL uses a sophisticated suite of tools that combine 3D visualization, command sequencing, and error checking. In this talk, he'll go into the tool set, talk about what it takes to drive a Mars rover, and discuss the particular sets of instruments that the rovers carry to enable navigating unknown terrain. The focus will be naturally on Perseverance, which landed on Mars 6 months ago and has driven over 1 mile from its landing site. He's also going to cover what the rover's been up to in that time frame, the successes of the Ingenuity helicopter, as well as the mission's first and many sample caching activities. Evan, it's all yours. I'm going to stop sharing and you can take control. Everybody, please mute yourselves.
All right, thank you very much for the introduction, Spencer. And I'm glad you appreciate the title because I worked really hard on that one. So I'm glad it's appreciated. Let me take over the share screen here. Yeah, you should be seeing my whole screen here. Let's go full screen. And we'll pull up the chat. So for Q&A here, I'll keep it up so I can take a look. If you guys have questions during the talk, go ahead and put those questions in the chat. I might try and answer them as I go, but if not, we'll get to them at the end of the talk here. As Spencer mentioned, my name is Evan Hilgemann. I have been a member of the Los Angeles Astronomical Society for a number of years now. So I'm quite excited to finally be able to give a talk to you all. I think this will be a lot of fun today. As was mentioned in my introduction, one of my primary roles right now is driving the Curiosity Mars rover, which has been on Mars for 9 years now. We actually just celebrated the 9-year anniversary. But today we'll be talking about Perseverance and kind of the shared set of tools that we use for the rovers. So a little bit more about myself. I'm actually in a group at JPL called the Technology Infusion Group, which it's a fun thing to say, if nothing else. At places like JPL, let me bring up my pointer here for good measure. You have a lot of people doing new technologies, coming up with new ideas, different ways of doing things that are oftentimes really cool and beneficial. You have a lot of people doing flight implementation. The issue is that they don't always talk to each other. You kind of have this big chasm in between the two areas. And then I try and be somewhere in the middle of those two. So try and identify, the high value new technologies and actually get that implemented on new missions. And that's a lot of fun for me because it means I get a lot of exposure to both this new technology development as well as flight spacecraft like the Mars Science Laboratory, Curiosity, and Perseverance. So that is enough about me. Let's talk a little bit about Mars. To understand the present day on Mars, I think it's useful to understand a bit about Mars's past. As many in this group are probably aware, if you went back 100 years, Mars would probably look something like this to you. This was a map drawn by Percival Lowell in the early 1900s. He spent a lot of time staring at Mars and was convinced he could see these long, straight features across the planet. He interpreted those as canals and likely evidence of an advanced civilization on Mars, maybe trying to pull water from polar regions down to a dry equatorial belt. Nobody else really saw these canals, so his idea never really took off in the scientific community. But this was very much the idea that a lot of people had of Mars all the way up until the 1950s and 60s, when we finally sent spacecraft there. So this is a picture from the Mariner space probe, or one of the Mariners, probably Mariner 4 in the 1960s, another JPL spacecraft I'll mention, the first spacecraft to fly by another planet. And a lot of people wanted to see if Mars was actually a planet capable of supporting life like we have on Earth. And instead of seeing a lush planet like our own, we found a planet that was more like our moon. a dry crater world, a very desolate surface, and nothing that obviously had a lot of life on it like we had here on Earth. After the Viking landers kind of confirmed those suspicions in the 1970s and 80s, there was kind of a big lull in Mars exploration until the 1990s. And today we have a much better understanding of what it's actually like on Mars. We don't have any forests or present day oceans or anything like that, or canals. But you have some other interesting features. We have the largest mountains in the solar system over on the left here. Those are ancient volcanoes. The biggest canyon in the solar system right in the middle here. That's over 2,000 miles from edge to edge. So that would stretch all the way across North America if it was here on Earth. So this absolutely dwarfs our own Grand Canyon. And if you start looking closer at the surface, you see other interesting things. A lot of scientists think that if you go far enough back on Mars, it may have looked something like this. There's a lot of debate as to like how much Mars had at different times in its past, and whether or not this global ocean is actually a realistic depiction or not. But we do have a lot of evidence that indicates there's a fairly large amount of water on Mars for a long period of time in its past. Now, what's interesting about this from a scientific perspective is that at the same time Mars would have been wet like this, we had life was evolving on Earth. We had single-celled organisms in the ocean, and this was 3 to 4 billion years ago. The issue is that we no longer have access on Earth to that geologic record. All those rocks have basically been recycled back into the crust of the Earth. There are only a few places on Earth where we really have an idea of what the geology of the planet and what the environment of the planet was like 3 to 4 billion years ago. But the entire surface of Mars is basically that old. So one of the big motivations of going to Mars is to learn what the environment might have been like on an Earth-like planet, 3 or 4 billion years ago, where life was initially evolving at. That's something that we actually can't study on our own planet, and we have to go to a place like Mars to learn about. There are any number of other good reasons to be studying other planets in our solar system. I'm an engineer, not a scientist, so I'm not going to get into that too much and say, well, we'll focus more on the engineering side of the rovers. But if you guys are interested in talking about science, we can come back to that in the Q&A at the end. Now, if you want to explore the surface of a planet, ideally you want a rover because that allows you to move around on that planet. You aren't just stuck in one spot. And I like to show this series of images because it indicates that rovers are not a new idea. I think a lot of people have this idea that we really invented rovers in the 1990s and have gone from there. But even as far back as the 1960s, people like JPL and other organizations were trying to figure out how a rover on another planet might work. And eventually you see this evolution up until the 1990s, where you get closer to what we currently recognize as our family of Mars rovers. So here's the family portrait of JPL Mars rovers. We have the Sojourner rover, which landed in 1997 as part of the Pathfinder mission. That guy's a bit bigger than a toaster oven. And it was really launched as a technology demonstration mission. It had some science capability, but the main thing was just to prove that we could rove a robot around on another planet. And I see that you are not seeing the whole screen. What part of the screen are you guys not seeing, if someone can chime in?
I can see the whole screen.
Can you see? Okay. Somebody commented that they aren't seeing the whole screen. So
I see Jet Propulsion Laboratory, but not underneath it.
When you had the four pictures, the slide before this one,
yeah,
I can only see half of the two on the right, and that's much better.
Is it all right for you guys? Or let me just try and exit out, and we'll stop the share and share again.
We saw everything on our screen here. So
yeah, we were seeing it all. It was okay.
Maybe it's on my end. I'll check.
Okay, well, I'll just keep going. Apologize if there are any issues, but thank you for bringing that up because I have had issues sharing screens before, and it's much better to know about it beforehand.
That looks better to me now.
Okay, great. So let's see, we're talking about rovers. We have a family portrait here. We were talking about the Sojourner rover. That was originally a technology demonstration mission. And it really paved the way for these larger and more capable rovers. We have Spirit and Opportunity, which landed around 2004. Small vehicle-sized rover Curiosity in 2012, and of course Perseverance more recently. And I'm mainly going to be talking about these larger rovers today because it's the more recent ones and the ones that I am more familiar with. One thing I want to be clear up front is that none of these missions are life detection missions. We don't carry the instrument suite that you would need to directly detect life on Mars. What we're looking at is more what was the environment like on Mars? Has Mars ever been habitable? Could it potentially still be habitable today? So the main thing that the instruments on these rovers are doing are interrogating rocks, looking at molecular makeup of rock specimens, and really trying to figure out what the history of Mars was, what the environment was like, and not necessarily trying to directly detect life. And that's a common misconception. And I'd just like to clarify it up front here. So now that we've talked a little bit about the rovers, let's talk about actually landing on the surface of Mars and choosing a landing spot in this case. This is the landing area for Perseverance. You can see the blue circle is where we knew the rover was going to land somewhere in that area, or at least had a very high confidence in that happening. And when we're choosing a place to land a Mars rover, there are a number of things you have to take into account. One of the more important things is actually the elevation of that locale. You actually want a very low elevation, and the reason why is because Mars has a thin atmosphere, and you want to put as much of that atmosphere between the surface of the planet and space as you possibly can, so you can slow down more. You want an area that's mostly flat. That's changing somewhat these days. Perseverance had a hardware package called Train Relative Navigation, so it was actually taking pictures of the ground as it came down and could avoid these cliffs and craters and other hazardous areas. But from an engineering standpoint, we like things to be relatively flat because it's easier to land in those areas. And you also want the area to be scientifically interesting, right? So a big flat plane might be easy to land on, but it's not as scientifically valuable. Here in Jezero Crater, you can see the crater rim on the left here, and the remnants of an ancient river that we know used to flow into that crater, and this large river delta. So for a long period of time, there's basically different parts of Martian geology were flowing down this river, being deposited in this crater bed, and that's one of the main science motivations of Perseverance, is to actually investigate this river delta, and in doing so, get a nice cross section of the history of Mars. And getting to the surface of Mars is, well, it's rather inconvenient, as I like to describe it. I mentioned earlier that Mars has a very thin atmosphere. The issue is that Mars has enough atmosphere to be a problem, but not so much to actually slow you down enough to get to the surface. So that's where you see the series of technologies being deployed when we land on Mars. This is the Perseverance entry. You can see the heat shield there, which we have to use when we hit the top of the atmosphere at a couple, I don't know what it is, 10, 20,000 miles an hour. You have to deploy a parachute to slow you down even more after that heat shield is done. That'll slow you down to maybe a few hundred miles an hour, which still isn't enough. So Perseverance and Curiosity finally used a sky crane to slow down all the way to the surface. They basically got lowered down on cables, suspended from basically a jet-powered backpack to get down to the ground, which is a very unique system. I'm not going to go into any more detail on what we call EDL, or entry, descent, and landing, but there's great videos out there on all of these phases of flight. So if you haven't seen those yet, definitely recommend going and checking that out. And once we get on the ground, we can eventually start roving around. This is, my job on Curiosity is basically a rover driver is understanding the mobility system and how it works, as well as the robot arm. The hallmark of our rovers at JPL is what we call this rocker bogie system. And it's shown a little bit better in this image. This is basically a test bed rover in the Mars yard at JPL. When people are saying the rocker bogie system, they're referring to this suspension system, if you will. There's this link, which is one basically rigid link pivoted right there. That's a rocker. Then you have another bogie back here, which is another pivot, and a similar setup. Then you have your wheels, of course, on the ends of each of these, and that is beneficial for a number of reasons. You can see in this picture how that front wheel is up on top of a reasonably large rock. but it's still keeping the rover itself fairly stable. It's not tipping and tilting a whole bunch. It's also what we call kinematically determinate, which is a fancy way of basically saying you always know what the position of the rover is going to be based on the position of the wheels. It's very good at climbing rocks, as you can see here. And it's entirely passive. So there are no springs or dampers or anything like you would see in a typical vehicle suspension here. So it's also very simple. So we really prefer this configuration. There are other ways you might see this done, but this is definitely the JPL solution to the problem. Before we talk more about how to actually drive the rover, it's useful to talk about the cameras because they're very, very closely involved in driving. These pictures are all from Curiosity. It's a similar set of instruments for Perseverance. Up on the masthead here, you have, starting with the smaller cameras on the outside, we call those our navigation cameras, or nav cams. They're basically delivering wide field of view, but lower resolution images that we directly use for driving. You can see they're coming in a stereo pair, so it gives us 3D information, which is necessary for mobility. You have these other cameras that are more inboard. Those are our master cameras. They're ostensibly science cameras. They're color, they're higher resolution. They're there primarily for science reasons, but we of course use them for driving too because we can see more detail further away. Up on the top here, you have what's called the ChemCam instrument. This is actually a small telescope. So you guys will appreciate that. You can see in the back of the telescope, that's essentially your mirror. This is a laser instrument. So this guy can shoot a laser, focus a beam something like 30 or 40 feet away, burn off a little bit of rock. And from the light that is emitted from that rock, it's able to collect that light in this telescope, perform spectroscopy on it, which is something you all might recognize from astronomy. Basically looking at the signature of that light. And by doing so, you can tell what that rock is made out of. So we can basically tell the elemental composition of a rock from up to 30 or 40 feet away. We have other engineering cameras near the bottom part of the rover. So this is the belly of the rover. These are hazard cameras, or HazCams. So they give us a really good view what's right front or behind of the rover. And then we also have science cameras out on the end of the robot arm. So this guy's called Molly. That's on Perseverance. I'm sorry, this is on Curiosity. Perseverance has a similar camera called Watson. But for driving, we're normally using these cameras up on the mast and the HazCam. And then I have a slide here specifically for this group because I thought you all would appreciate some of the amateur astronomy that we're able to do from Mars. If you haven't guessed so far, this animation on the left, or this video, it's not animated. That yellow disk is the sun, and this black potato looking thing, that's the moon Phobos, actually eclipsing the sun. And we occasionally get opportunities to do experiments like this. So there is science value in taking this sort of video from Mars. We've occasionally looked at stellar objects for various reasons as well. And we actually use the sun for navigation too. There's no magnetic field to really speak of on Mars. So we can't use a compass like you might on Earth to get our orientation. So occasionally we actually have to use one of our cameras to look up at the sun to basically verify what direction the rover is pointed in, make sure our understanding of that has not drifted too much over time. And another thing, so now that we've covered cameras, let's talk more about what it takes to drive the Mars rover. So one of the misconceptions I get fairly frequently is that we can drive the Mars rover with a joystick or something resembling an Xbox controller. And that's very much not the case. The issue is, again, many people in this group are probably aware of, Mars and Earth are very far away from each other, anywhere from 33 to 250 million miles. Right now, we're pretty close to that max distance. Actually, Mars is almost on the other side of the sun from Earth. And even traveling at the speed of light, that takes up to 22 minutes to cover that distance, which is, of course, way too much time for any sort of real-time communication. So basically, the way this works instead is that we bundle packages of instructions by day. So we'll send a whole day's worth of instructions to the rover. So we might transmit instructions in the Martian morning. The rover normally wakes up around 9 or 10. It'll listen for instructions. It'll get those instructions. It'll go off and do its thing during the day. And then sometime during the day or the end of the day, it'll basically transmit back to Earth and tell us what happened. And most of the time, that's more or less what we expect it to. Sometimes it's not what we expect it to, and then we have to deal with that the next day. Now, this would work perfect if Mars and Earth were perfectly synced together. But the issue is Mars has a slightly longer day than on Earth. A Mars day is about 40 minutes longer than an Earth day. So the two planets aren't really synced together. So for the early parts of the mission, like the first 90 days of the mission from when Perseverance landed in February until about May, the operations team was actually working on Mars time. So they went to work every day about 40 minutes later, and that allowed them to do their work on, I'm sorry. They were basically working on Mars time. So they were generating instructions for the rover while the rover is sleeping. And then when the rover was awake and doing things, the people on Earth were sleeping. Now that's very good for the rover productivity. It's less great for the people on Earth. So what happens later in the mission, after the 90 days, is the Perseverance team is still working 7 days a week, but sometimes they have to transmit 2 days of instructions at a time to kind of deal with this the time difference. On Curiosity, we've been on Mars long enough now. It's not uncommon for us to do 2 or 3 day bundles of instructions at a time. Now I want to talk a little bit more about what driving the Mars rover actually looks like and the tool set we're using. I can't talk too much about the actual language we use to talk to the rover because that's all export controlled, but we can show some of the cool animations we work with. So you can see here we have a 3D rendering of the rover in space, which is kind of cool. But basically our simulation software allows us to take that rover and put Mars underneath it. So remember those navigation cameras I talked about earlier? They'll basically scan the terrain, take a bunch of pictures. Our computer software is able to take all that imagery and combine it into what we call a terrain mesh. So we're able to see what the rover looks like relative to its terrain. We can see where there are tall slopes or rocks, like over here, maybe a sand pit in the area. And then my job is basically to take this information, take whatever sort of goals the science team has. Maybe there's a cool rock over here somewhere we want to look at. And then I will take a look at this and try and figure out a safe path for the rover to drive. We can put some waypoints down, put some keep in and keep out zones. So say if we go inside this red circle, then we'll fall out the drive and the rover will just wait there for more instructions. And then what's really cool about this software is we can actually simulate the entire drive, see what it looks like, and play it all back in an animation. Our software is actually running a full version of flight software. So we're generating all the commands. We're simulating every single command that we send to the rover in this software environment. So we have high confidence that this simulated rover will behave as the actual rover would on Mars. And then because of this terrain mesh, we're basically driving our rover on top of that mesh. So if we're going over a big rock and it causes that suspension to do something funny, we're going to see that. So this is kind of the crux of my job, is developing, safe sets of instructions for the rover to execute while still, meeting the science goals for whatever we're doing. Now, to achieve a path like this, or to do a drive, we have a few different options for how we actually command the rover to drive. The first one I'm going to talk about is blind driving, and I can't think of a picture to go with this. We're just going to leave the slide blank because it's blind. This is basically when the rover closes its eyes, doesn't take any pictures. It's just going to try and make a commanded amount of distance or range by wheel odometry. So it knows, if it spins its wheel this many times, it'll go this far, and it's just doing that commanding. So I might tell the rover to go 30 feet forward, turn 45 degrees to the right, and then go another 10 feet or something like that. It'll basically just spin its wheels the right amount of times to accomplish that distance. Now, the useful thing about blind driving is that it's fairly quick because we're stopping to take pictures or anything. But it's also not very accurate. So you can have issues, or maybe if you're going through a sandy area, or an area with loose soil, the wheels might start to spin a little bit, and maybe you don't make as much forward progress as you want, or maybe the rover turns a little bit, or slides a little bit, and we aren't going to pick up any of that. So our most common kind of driving is actually called visual odometry. In this case, instead of just going blind, as we call it, about every meter, the rover will stop and take a set of pictures, again with those navigation cameras. It has software on board that's able to analyze the terrain, look for unique 3D features in that terrain, and then compare one set of images to the previous drive step. So, the set of images from here to the set of images 1 meter ago. And from looking at those two images, it can tell exactly how far forward it went, if it moved at all. And it's smart enough to do some adjustment and try and stay on a pre-planned course. It'd be like, instead of, if I wanted you to walk across the room blind driving, you would just close your eyes and do that. With visual odometry, it'd be like you would take 2 steps forward and then open your eyes and see where you're at, make an adjustment, take another 2 steps, open your eyes, and so on and so forth. Now, the type of driving that probably gets the most press, but we don't use too much on Curiosity, is called AutoNav. AutoNav is basically another step above visual odometry, and that in this case, the rover is actually going to take a bunch of images of the terrain and create what we call a hazard map. It's basically going to mark areas that are not safe to go on as red or orange, and the safer areas are, of course, going to excuse me. The safer areas are going to be green. So we might give it a general direction to go to, but then leave it up to the rover to pick a particular path through that area that's safe. We're using AutoNav when we want to go further than what our cameras can see. So you remember that mesh I talked about from earlier? We can only use visual odometry and blind driving if we're on that mesh, which maybe we can only see 30 or 40 meters away. And if we want to go further than that, we use AutoNav. Now, AutoNav on Curiosity is very expensive because you have to take lots of pictures and it slows you down a lot. Perseverance can actually do AutoNav much faster. So this is the first AutoNav drive on Perseverance. This rover is actually able to do something called thinking while driving due to the way the electronics are set up. So on Curiosity, we basically have to stop and take pictures and do a bunch of computer analysis. Perseverance is able to do all that while in motion. So it's quite an advancement forward, and because of that, you're probably going to see a lot more AutoNav driving on Perseverance than we've ever done on Curiosity. So now that you know a little bit more about driving, I want to focus on the Perseverance mission, and let's talk a bit about what it's up to and where we're going next with that rover. So this is a map that's available on the internet. If you guys just Google search for "where is Perseverance," you can get to an application that will basically give you this map. We landed up in this area, and that white line is basically the traverse path of the rover so far. And you can even see here, they were doing a lot of longer drives through there. That's actually when they started to use AutoNav on the rover. And this other line is the path of the helicopter, which we'll talk about a little more as well. They've basically been working their way to the south here. There's a lot of interest in sampling the rocks in this area because it's going to be the oldest rocks that they'll be able to see on the entire mission. Remember that the rest of the mission, they're basically going to backtrack up and around this sandy area. Sand is bad for rover traversability, so we generally stay away from those areas. And then going up into this ancient river delta. And at that point, you're going to see newer and newer rocks. And there's a lot of desire to really understand what things are like in the base of this crater. So let's talk a little bit more about the Perseverance rover itself and look at the instruments that are on the body of the rover. We have one instrument down here called MOXIE. It's actually a little technology demonstration. It's able to generate oxygen from the carbon dioxide atmosphere of Mars, basically by separating off this carbon and being left with oxygen. It works very much like a fuel cell does, but backwards. And is very useful if you ever want to send people to Mars. You can imagine it'd be useful to be able to generate oxygen from the atmosphere. And that guy is actually funded by the Human Exploration Office of NASA. We have a cool instrument called RIMFAX on the back, which is able to use subsurface radar to look something like 60 feet under the ground and understand what the rock structure is below the rover. We have the Mastcam Z. The Z stands for zoomable panoramic cameras. On Curiosity, the Mast cameras are basically fixed magnification. On Perseverance, they're much higher resolution and they have zoom capability. We have Meta, I'm not sure how to pronounce that actually. That's our weather station. So measuring things like temperature, humidity, wind speed. That's what these little appendages are on the mast, our wind sensors. Understanding the environment of Mars. And there's another instrument up on the mast here called, they call it SuperCam, but it's the same as our ChemCam on Curiosity. It's able to shoot a laser out and understand the composition of rocks from the behavior of that laser. Now what I want to spend a bit more time talking about is the Ingenuity helicopter, which was tucked underneath the rover for landing. It was deployed from the rover fairly early on in the mission. So you can see that it was tucked up underneath here, basically unfolded from the bottom of the rover and basically left on the surface. The whole point of Perseverance is it's another technology demonstration mission. I'm sorry, the point of Ingenuity, not Perseverance. Ingenuity is a technology demonstration mission. And the idea being is that we want to prove that it's possible to fly an aircraft in the atmosphere of Mars. Mars again has a very thin atmosphere, so it's hard to fly. And we want to prove out this capability. And so remember, in the same way that Sojourner rover back in the 90s was a technology demonstration mission that led to larger and more capable rovers, we're hoping that this helicopter demonstration mission can lead to larger and more capable helicopters going into the future. And we've had quite a bit of success with this little helicopter so far. The first flight, they did prove it was possible to fly on Mars, flew up something like 15 feet in the air and just came back down. Got a little bit sportier on the second and third flights. They started flying up and then over and back. On the third flight, they got the only picture I know of the Curiosity, or I'm sorry, I'm getting my rovers mixed up here, of the Perseverance rover from the helicopter, which is a really cool shot. On the fourth flight, they started going further afield. This is actually an image looking down from the helicopter. So that's the shadow of the helicopter on the ground. And they were basically mapping out terrain at this point because they wanted to find another spot to fly to and then land at. And that's indeed what they did in the fifth flight, was move the helicopter to another landing spot. So now we're up to 10 successful flights of the helicopter, which is pretty good since the success criteria for the helicopter was to complete five flights and survive for about a month on Mars. The helicopter was never really meant to contribute to the science output of the mission, but at this point it survived long enough and is healthy enough. It is actually going out in front of the rover, scouting out the terrain ahead of time and helping the scientists decide where to actually send the rover next. So it's definitely a very cool capability to have along with the Perseverance rover. It's unclear how long it will actually survive, but hopefully it will indeed lead to larger and more ambitious flying vehicles on Mars and other planets. So now let's go back to this diagram of Perseverance. I haven't talked about what's on the end of the robot arm yet. We have a couple instruments out there called Sherlock and Pixel. Also the Watson camera, some very contrived acronyms out here on the end of the robot arm. These are all spectrometers. Unlike the other spectrometer I've talked about, these are contact science instruments. They have to be very close to the ground. And they're basically looking at both the elemental in the case of Pixel and the molecular composition of rocks on the ground in the case of Sherlock. And the unique thing about these instruments compared to what we have on Curiosity is they're actually able to show the distribution of various compounds and elements in the rock. So that's very cool. If you're looking at something like this is not a picture from Earth. It's not a picture from Mars. It is a picture from Earth of an ancient microbial bed, which would be, a gold find on Mars, of course, if you found something like this. But to be able to look at something that's stacked up like this and tell you exactly where organic molecules are in that cross-section of rocks. Similarly with Pixel, but with elemental compositions. This is something we've not been able to do on Mars before. Our instruments on Curiosity are basically giving us just bulk composition information back, it's not separating it out into individual regions like this. So these instruments are a very cool new capability that we have on Perseverance. And I'd be reticent if I didn't talk about this big thing on the middle of the turret, our drill on Perseverance. One of the major goals of the Perseverance mission is to collect rock samples from the surface of Mars with this drill. The drill is going to collect what's called a rock core. So the drill bit itself is hollow. It'll drill out a cylinder of rock that's, I don't know, about as big as my pinky, a tube of lipstick, something like that. So we'll drill out that cylinder and then deposit it into the front of the rover. The front third of the rover is this heinously complex device called the sample caching system. Its job is to basically take those samples, process them, hermetically seal them in metal tubes, and then place those tubes on the surface of Mars. So they'll probably be all cached in one area. And that might not seem like a super intelligent thing to do, but the idea is that we'll then go with another rover. This rover is actually being built by the Europeans. I call it the Fetch rover. I don't know if that's the official name of the rover, but it's basically going to go out and find these sample tubes, collect them, bring them back to another lander, which has a rocket attached to it. We'll transfer those samples into the rocket and launch them into orbit around Mars. At that point, they can be picked up by another spacecraft and brought back to Earth. And this is a big deal for the science community. People have been talking about Mars sample returns since the 1970s, and we're finally now seeing it happen. And this is a big deal because there's a lot we can't do when we're just sending a rover to Mars. We have very limited mass and volume. We can only send a few instruments. If we bring these samples back to Earth, we can basically send them all over the world and use all the science capability that we have on this planet to analyze those samples. And you're able to learn much, much more about the present state of Mars and the geologic history of Mars by doing that than just sending rovers. And now the next question should be, well, how is that going so far? We've been on Mars for what, 6 months now? Perseverance actually drilled its very first drill hole. This was just over the weekend. So this is all hot off the press. You can see the hole here, an anthill looking thing with a hole in the middle. That's the drill hole. The drill finds around the outside. And again, they were interested in looking at this rock because this is the oldest rock that they're going to be able to see on Mars. As I see Mark made a comment about where did the core go in the chat. And that's a great question that I don't necessarily have the answer to. With this first drill hole, they were unsuccessful in actually getting that core sample. So this is a picture looking at the very end of the drill, basically looking down into the hollow drill bit. As you might be able to see, there's nothing inside of that drill bit. From what I've been told so far, they think it's probably an issue with the geology of the rock, and it doesn't seem like there's any issue with the mechanical or hardware system itself. I don't have any more information on that than what's been released in the press, but this is something that's happening right now. So I think now is a really exciting time to be part of Mars exploration, be paying attention to this sort of thing. This is again a decades-long ambition to collect samples from the surface of Mars and bring them back to Earth, and we're now seeing that play out in real time. With the faults and successes that you would expect with an ambitious endeavor like this. So I'm certainly very excited to be part of the Mars exploration team at this time, and I hope you all are excited to be here and be part of this as well. So as I wrap up here, just a couple more resources. If you want to follow along with the mission, mars.nasa.gov is where to go. Again, if you want to see that map that I showed earlier, just go to Where is Perseverance? Google that. It'll take you right there. You can also see all the Perseverance raw images. If you search for that, that will take you to a different website. And feel free to stay in touch with me as well. Again, my name is Evan Hilgemann. I'm at Evan Hilgemann on social media, and that website or the newsletter I run is called Explore and Observe. That was mentioned in my bio earlier. But I basically write a biweekly newsletter on modern day exploration of Earth and space, which is something that I'm very passionate about and something that I imagine a lot of people here are interested in as well. So that's something to do for fun. Feel free to check it out if it seems interesting to you. And with that, I think I can start taking Q&A. I see there are a few questions in the chat, so I'll start there, and then maybe we'll switch back and forth with any live questions that people have. Is that all right? Spencer, how much time do we have at this point?
You've got probably about 45 minutes.
I have 45 minutes left.
No, well, I think we generally we budget until 8 o'clock, until 10 o'clock, but historically we've closed about 8:30 or 8:45. I'm sorry, 9:30.
Or 9:30?
Yeah.
Okay, well, I'll start answering questions here, and then if you guys want to jump in to close the meeting, just do that. How about that?
Okay. By the way, I just posted the door prize link in the chat, so please register. We've got about 35 people out of 46 have registered.
Okay, so I'll start again with the questions in the chat here. Let's pull that up. Whoops, let's back up slide. Okay, so starting at the bottom here, I did not see solar panels on Perseverance. Can you describe how the rover is powered? Both. So let's actually go back to the slide I had with all the rovers up front here. Yeah, so both Sojourner and Spirit and Opportunity, they're all powered with solar panels on the deck. That's disadvantageous on Mars for a number of reasons, mainly dust. Is not your friends. Those panels will get coated in dust. Spirit and Opportunity got lucky in that the wind occasionally cleaned off their solar panels. But both Curiosity and Perseverance actually have a nuclear power pack in the back. So we don't have one on Earth here. But there's basically a brick of plutonium in the back of the rovers. All that is doing is generating heat, and we're able to harness that heat to make electrical power. You can basically make power from that heat differential. The interesting thing is it's not very much energy at any one time. The power supplies on these rovers are putting out about 100 watts of power continuously. So that's about as bright as a bright light bulb that's above me in my ceiling fan here. That's not very much. So we're basically continually charging the batteries, and then doing all our power intensive activities off the batteries. That does mean you have to slow down on occasion. You have to stop, let the rover rest, and recharge its batteries. But it's also a very reliable source. Let's see. I will do another one from the chat here. Okay, Arun asks which RF frequency band is used to communicate the rovers. I honestly have no idea. I'm not going to pretend to answer that question. I think it's a UHF band that's the downlink, so from Rover to Mars. I'm not sure what bands we're talking on going from Earth to Mars. Are there any questions that are not in the chat before I keep going through the questions in the chat? Does anyone want to jump in?
Sure. I had a question about the navigation, about the driving. So you have combination of blind and then visual odometry. Do you do combinations of both? And then do you basically, when you're doing your mapping out the plan for the path, you send a combination of instructions that incorporate both and just hope that you made the waypoints?
Yeah, so we can combine all those different drive modes on one drive. So what's typically what we're typically doing if we're, say, doing an autonav drive is we're probably driving to the edge of that mesh in either VO or blind driving, and then we can transition to autonav at that point. So yeah, it's possible to have 3 different modes of driving, and we're able to elegantly transition between those modes in the middle of a drive. You just need to be careful about your uncertainty values at that point, because if you're doing a long leg blind, and then you're using VO after that, you have a lot of uncertainty that's built up in that blind leg that you have to account for to make sure you aren't going to hit any hazardous rocks or otherwise. Does that answer your question?
Sure. So then I guess if you're seeing any drift, you can use a visual odometry to correct for that.
Yeah, so that might be a scenario where we're, say, on a steep slope, doing like 15 degrees cross slope and it's kind of sandy or something like that. The rover has a tendency to slide downhill. And yeah, if we're using visual odometry, it will sense that downhill slide and it'll be able to correct for it to the best of its ability. And that's definitely a very useful and powerful feature to have. We again, the vast majority of our drives on Curiosity are done with visual odometry. And I want to thank Mark Schaefer for answering the communications question, X-band for direct Earth communication, and UHF to orbiters. So yeah, when we're doing downlink, when we're getting information from the rovers, all that information goes through the orbiters around Mars. When we're talking to the rover, we actually talk directly from Earth to Mars, or to the rovers, to provide a bit more background on that. Okay, what kind of training and background is needed to be a driver? From, it looks like Pablo Lewin. That can actually vary quite a bit. It's useful having a cross-disciplinary team. So my background is, I actually have an undergraduate degree in mechanical engineering, a master's degree in aerospace engineering. I did thermodynamics in undergrad, I did some mechanisms work, I did guidance and control in grad school. I got hired at JPL to build spacecraft structures, and now I drive a Mars rover. So it doesn't necessarily have to be a linear path. But we have some people like myself that are more heavily involved in the mechanical engineering and the robotics side. We have a lot of people who are very much computer science oriented and software oriented. And they're of course very useful to have around because all the coding is basically, or all of our instructions are generated using software. And you have people who are more from the systems engineering realm, and even the science teams as well can become rover drivers. As far as the training to become a driver, it's fairly intensive. So I've trained for about 1.5 years to basically finish all the training to become a rover. There's a lot that goes into both learning the tool set is one thing, because it's a very large, complex set of tools that we use to drive the rovers, and also understanding all the different scenarios that you might end up in, how to deal with those sorts of scenarios, what sorts of tools that we have at our disposal to take care of the rover on Mars and operate it safely. So lots of varied backgrounds are on the team, and then it's a lot of training of all those people, common training to make sure everyone understands how to operate safely. Okay, I see there are a bunch of questions in chat, so let's go through a couple of those. So David, I don't know your last name, David, but you asked, where does the signal leave Earth from? Goldstone tracking stations, etc. That's a good question. NASA operates a set of antennas around the world called the Deep Space Network. There's one set of antennas in Goldstone, which is up about 3 miles north of here in the desert, in the Mojave Desert. There's another set of antennas in Spain, another set in Australia. They all have similar capabilities. So what that means is that no matter where you are in space, you should be able to talk to at least one of those ground stations. So all of our commands are basically going out through those antennas and also coming back through those antennas. And having antennas around the world like that can lead to interesting scenarios. We had an issue this last winter where the antennas in Spain got knocked out by a blizzard. We got like 6 inches of snow. They never get that in Spain. Basically knocked out the antennas, and then we didn't get the information down from the rover that we were expecting because the ground station was down. So it's a very, very valuable resource, of course, but there are interesting intricacies in working with it. And let's see here, Mike Portis asks, when coring for rock samples, how deep can Perseverance drill? I'm actually not entirely sure of that off the top of my head. The core sample it collects is going to be, probably 5 or 6 centimeters long. So the example I hear is, about as large as a finger or a tube of lipstick or something like that. So you aren't going particularly deep. You're in that 5-6 centimeter range. And let's go up to the top and take a look at some that were asked earlier and I didn't get to. So where did the core go? That was a good question. Can you briefly discuss cleaning innovations for dealing with Martian windstorms, particles coating the solar panels? So that goes back to we don't have to deal with that as much on Curiosity and Perseverance because they don't have solar panels. Spirit and Opportunity basically got lucky. Those missions were originally 90-day missions. And that was because people thought the dust would collect on the solar panels. And basically, you wouldn't be able to get enough power after 90 days to drive the rovers. But they found that the wind was actually cleaning off the dust from the panels, which allowed the missions to last 6 and 12 or 13 years in the case of Opportunity. There are, of course, other landers and other rovers on Mars too, the Chinese rover that are solar powered. And there's really no good method to clean those panels. So it's something you have to plan for and understand that could be a limiting factor in your mission. And let's see, how was the age of the rock determined from Arun? That's actually, I'm not sure how to answer that off the top of my head, to be honest with you. Again, I'm on the engineering side and not the scientist, so I'm not sure off the top of my head what methods they use to constrain the age of rocks on Mars. That's a good question. I might look into that, and maybe with some of these questions I'm not as sure on, I can put something in the LIS newsletter with some general questions. That would be, I think that'd be useful. Are there any other live questions we have before I keep going through chat here? Anybody else want to ask something?
I have one question, if that's okay.
Yeah, go ahead, Claude.
Okay, here's a really ignorant question. I still don't quite understand the drive suspension system.
Yeah.
The bogies pivot. How I still don't quite understand how the rover stays level. I believe you said it's completely passive. Is it just that the center of gravity is below the pivot point, or is there something that actually?
Yeah, not exactly. Well, I think it's below this pivot point. I'm actually not sure whether it's above or below exactly. The way this works is you have your rocker, which is green here. You have your bogey. Let's turn back on our laser pointer. You have the same thing on the opposite side. And then those are actually connected over the top of the rover in the case of Perseverance and Curiosity. So let's go back to that other image. This bar on the top, that gray bar, is actually connecting the suspensions on the two sides of the rover. So if say this rocker on the left side of the rover pitches forward, it actually causes the rocker on the other side to pitch back by an equal amount. And that's basically the secret sauce of the suspension, you will, that allows it to stay constrained and fairly level. It's not going to be perfectly level because if you're on a slope or something, you're at that angle.
Okay, now that helps a lot.
On the big rock,
I've never quite understood that. Thank you.
Yeah, but that's basically what's doing the work there. Any other live questions here?
Yeah, Evan, you mentioned that you're basically using a combination of technologies to keep the Perseverance from running into rocks or going in the wrong place. So let's call that some level of basic AI. Is that happening in real time? I mean, is the Perseverance able to, use image data and predetermined point that it needs to get to so that it can say, I need to go from A to B, but oh wait, C is in the way, and it automatically moves around that hazard? Or is that something you as a driver have to deal with? Once again, not in real time because of the delay.
Yeah, so there are a couple ways to look at that. When we're doing blind mode or visual odometry, that's what we call directed driving. So we're basically saying, as the rover driver, it's our job to identify the hazards. The rover is not looking for hazards in those scenarios. We're saying, take this direct path to waypoint A, and then you're going to turn, you're going to stay on this line to waypoint B to go around this rock, and then you're going to go, straight and do whatever. With AutoNav, that's where we're basically using AutoNav where we cannot see the terrain anymore. So in that case, we're giving the rover kind of a general goal. So we're giving it more freedom in the path, if you will. And we were saying, generally head in a westerly direction or something like that, and try and get 100 meters if you can. And then as it's going along, it will analyze the terrain, and it's able to detect things like large rocks. in its path, and it will take that into account, and it'll plan a new path that goes around that rock. So in general, we will use that capability, but largely speaking, the rovers they don't do a lot of things entirely autonomously. Most of the tasks the rovers do are directed, where we're giving it pretty explicit instructions for what it's supposed to do. It does that to the best of its ability, and if it can't accomplish that, if it faults out, if something weird happens, then it basically just stops whatever it's doing and waits for new instructions from Earth. Does that answer your question, Richard?
Well, I guess where my question was going with that is, and don't take this wrong, well, you're controlling you're driving it.
Yeah.
And you're saying go here, and you made a mistake, and there's I don't know, a rock, a hole, whatever in the way. Can it use its technology to say, oh, wait, no, I needed to go do this first?
Yeah.
Can it ignore you and fix a problem?
The short answer, I think, is no. So when we're doing directed driving, and by the way, that's a great question, because we are humans and we're highly trained, but sometimes people make mistakes, and we have systems to avoid that, but things do happen. Maybe that rock was a bit bigger than we thought it was going to be, or something like that. When we're doing directed driving, that blind mode, NVO mode, the rover is not analyzing the terrain to look for hazards. So it'll do exactly what we tell it to. And if we tell it to go straight for 80 meters, it'll do its best to go straight for that far. Now, the way that we protect the rover against the sorts of hazards that you talked about, say there's a big rock we didn't see, or a dip or something like that, we have a lot of what we call reactive safety checks, any one of which can cause the drive to stop or fault out. So like if the rover senses that one wheel is all of a sudden drawing a ton of current or something weird like that, it'll stop the drive and just wait for new instructions. And we have stalled motors on things before. If the suspension angle gets really high, more than a certain threshold, that'll cause the drive to fault out. If it gets to a higher tilt than we expect or allow it to, that'll cause the drive to fault out. So it's less of the rover actively responding, I guess, autonomously, and more of a reactive safety check that'll cause the drive to stop, and then we have to respond to it when we get that information back down.
Is there a technological reason that we couldn't incorporate both? I mean, does it not have the processing power to be able to do the AI at the same time you're saying go straight, and it says I can't go straight?
It can. So that's with the auto navigation capability, is basically the rover looking at the terrain and deciding on its own where it's safe to go and where it's not safe to go. Now, the issue with that auto nav capability is it's expensive to run, especially on Curiosity. If we're going flat out in blind driving mode, and these numbers are for Curiosity, we can make like 100 meters in an hour, top speed, in blind mode. With visual odometry, it's like 30, 40 meters in an hour. And if we're in auto nav, it's like less than 20 meters in an hour. And that's because it has to stop and take a lot of pictures and analyze those. So there's a lot of time during the drive where it's just sitting there and thinking. That's time we have to keep the mobility system powered. That's time that we can't spend doing other things. And there's more telemetry as well that has to come down. There are a number of costs related to using AutoNav. A lot of those are being reduced on Perseverance, as I mentioned, because they're basically able to both have that AutoNav capability and also drive at a faster speed, because they're doing that processing in parallel with the drive.
So at the end of the day, it does come down to the fact that we don't necessarily have enough battery power and or computing power to create what I would call true AI, even though you're driving it.
Yeah, we're oftentimes limited by power. Like maybe we only have enough power to drive for 1 hour. And maybe it takes an hour for us to drive to the edge of the mesh, and we don't have the time or the power available to go into AutoNav. Now, there are times where the main goal is just to get as far as we can, and then maybe we have 4 hours to drive, and we can utilize that AutoNav capability more. And I see a couple of questions related to this in chat, so I'm actually going to transition to,
Okay,
to that.
I do have a question when you're done with that, Evan. From
Okay,
David
yeah,
Atkinson.
let me keep going on this because there are a couple of related
Sure.
questions in chat. and then we'll come back
Sure,
to
go
you,
right ahead.
David.
Thank you.
So Pablo asked, have the newer design of the wheels on Perseverance performed better than Curiosity's? I'm guessing that's yeah, hose. Okay, so I'll rephrase the question, and our Perseverance wheels performing better than Curiosity's. And I'm guessing what you're getting at, Pablo, with that is Curiosity has had a lot of issues with wheel wear on the wheels. And basically something like 300 or 400 days into the mission, the operations team started noticing that we were getting holes in the wheels, that the sharp pointy rocks were in some cases puncturing the webbing on the wheel. And that's of course not what you want out of your Mars rover. That's not what was expected. That was due to a number of reasons, including how we actually command the rover, the terrain in Gale Crater where Curiosity landed was different than expected. From what I've been told, the terrain in Gale Crater, you have a lot of rocks that are basically just cemented into the bedrock that are very pointy. In the previous missions, the Spirit and Opportunity, the terrain that it came across was more like rocks loosely embedded in soil. So the terrain was just more hazardous than we thought. And there's also, let me go back to my mobility picture here. You can also see how there's this chevron pattern on the wheels. And that caused issues too. These sharp points create what we call stress concentrations, which can actually cause additional damage with the wheels. And one reason that relates to this AutoNav discussion is that AutoNav on Curiosity and to some extent on Perseverance as well, it can sense large rocks. So if there's a 40 centimeter, a 2 foot tall rock in front of you, it's able to see that and sense it, and it will avoid that rock. But if we have a bunch of small pointy rocks in front of the rover, it might decide that that's okay to drive on because it just sees small rocks. There's no part of that algorithm that's looking for pointy rocks as well. So when we're using the AutoNav on Curiosity, we have to have a fairly high degree of confidence that the terrain that we're driving the rover into is not going to be hazardous for the wheels. So we basically have to have a good understanding of what AutoNav is looking at and verifying that there aren't any hazards in a drive path that AutoNav can't detect. Another example is sand. So AutoNav, when it's looking at the terrain, it's largely looking at things like tilt and any large changes in height of the terrain, looking at rocks. Sand is one of the most hazardous terrains for the rover because you just can't get any traction in there. And AutoNav will happily drive the rover into a big sand dune and cause the wheels to spin and probably cause something to fault out. So we have to be aware of that as rover drivers, that is a limitation of AutoNav and something that we have to plan our routes around in many cases. And then the question was around, is Perseverance doing any better? And yeah, they basically did a redesign of the wheels for Perseverance. Let me get to one of the later images here. So you can see the wheels for Perseverance. They don't have that chevron pattern. It's more like a really shallow sine wave, so you don't have those stress concentrations. They're a little bit thinner and a little bit thicker as well, so they're much more durable. And the test bed team has done a ton of work on these wheels to make sure we won't have a repeat of Curiosity. So yeah, I'm highly confident that these wheels will wear much better than Curiosity. And there was, let's see, one other question somewhat related. Okay. Not necessarily. Okay, so David, why don't you ask the question, and then there's
Yes.
I'd like to answer this other one in chat.
Sure. Okay. How many times during our Earth Day do you send it instructions to drive, and how many feet would that be on Mars per instruction cycle?
What was the last part of that? How many
feet would that be after each
So
instruction?
like how far does the rover drive?
How far would it run? Yeah. How far would it drive in miles?
Yeah, so that's a good question. We basically have an opportunity to talk to the rover once every Mars day. So every Mars day, every SOL is what we call it, SOL. The rover wakes up at around 9:30, 10 a.m. And the first thing it's doing is listening for instructions from Earth. And we can basically use that opportunity to, the term is uplink, those instructions to the rover. And then the downlink, the communications path from the rover to Earth, as we mentioned before, actually goes through the orbiters that are orbiting Mars. So we'll get an opportunity to hear from the rover whenever a satellite's overhead and it's not busy doing other things. So oftentimes we'll downlink information from the rover 2 or 3 times in one Mars day, and we have the one opportunity to uplink in the morning. Now with Curiosity, we've been on the surface of Mars for a while now, so we aren't necessarily doing that planning cycle every day. So oftentimes we might have, if we work a normal 5-day week. So on Friday, we're putting together 3 Mars days worth of instructions for the rover, and typically just sending all of that at once.
Right. So the last question will be, how many feet would that move the rover?
Yeah. So typically when we're driving, it varies, depending on what the science priorities are. I think that was another question here. Yeah, I'll do that one next because it feeds into that.
So on average,
it's a combination of what their capability is, what science wants to do, and how well we can see the train in front of us. So the short answer to your question is, like a 30 to 50 meter drive. So that's say 90 to 150 feet.
Okay.
Is going to be that's a typical drive. We're only going to do 1 drive per planning cycle. So we're never going to send up 3 days worth of instructions and have there be 3 separate drives unless there might be some rare cases, but that's typically not the way we work. It's typically 1 drive every planning cycle, unless we're sitting down and drilling for 2 weeks or something like that.
Gotcha.
Yeah, so I guess that's what I would say is we're typically going 100, 150 feet in between, I guess, uplinks or when we're talking to or hearing from the rover.
Okay, thank you.
And that also plays into the question in the chat, which is how do we decide which direction to go? Are there destinations? Do you decide by committee? Or are you just wandering around randomly? I like that last part. Anyway, the answer to that is I'm not necessarily deciding on those priorities. I'm part of the engineering team, and the engineering team is in some ways to operate the rover for the science team. It's the scientists that are basically deciding where's the real high value geology here. Which rocks are going to be the most valuable for us to go up and poke with our contact science instruments. A lot of that is done on the day-to-day basis. That's done, I suppose, by committee. So at the beginning of our planning day, there's basically a big discussion with the project scientists from the different instruments. And they're deciding, what are our priorities for the day? Where do we want to drive to? Is there something particularly interesting in this workspace that we want a closer look at? A lot of that work is actually done what we call strategically, so a long time in advance, as opposed to tactically, which would be day to day. So strategically, we have what's called the strategic drive route. So we know that in general, we want to drive, along this particular, generally speaking, go in this direction, up next to this mountain, and then investigate this cliff over here, something like that. So we have that general high level guidance of, what is the goal of the mission? Where do we want to be in 6 months from now? And how do we get there? And that's, a big committee decision, I suppose, in advance. And then we're also taking direction from day to day in the sense of what are the science targets along this route? Now, what my job basically is oftentimes to tell the science team, what can and what can we not do? It's okay, maybe you want to go look at that rock, but there's a 30-degree slope right there and we can't get up that. Or you want to, look at this contact science with this rock with a robot arm because it's right next to us. But it's unsafe to touch that rock because it has all these nodules on it. And, there's a hardware safety hazard for that. So a lot of my job is taking the science priorities, understanding what that is, combining that with a very deep understanding of the capabilities and limitations of the rover, and trying to get as much high value science as we can out of the mission.
Evan, You
Yes.
mentioned just now, you mentioned strategic planning.
Yeah.
How often do you guys suddenly find something along the way that changes the strategic planning into holy crap, let's go look at that?
Yeah. So it's not too often that we make a very huge deviation from that strategic path that we've developed. Like we're kind of bouncing around along it, and we'll make, we might go 100 meters out of the way if there's something particularly interesting over here. Sometimes the science team will come together and basically say, we think there's a high value in going off in this different direction. So that actually happened last summer. We were trying to do a traverse. We were doing a traverse, and we're basically, with Curiosity, we're leaving one geologic unit, entering a new geologic unit, and the scientists wanted one more chance to basically sample the soil in this old geologic unit in an advantageous location. So we detoured quite a bit in that case off of the strategic path, and that was a big detour that took months to complete. So yeah, it's not too often that we're making huge deviations off that strategic path, but there's a lot of there's a lot of discussion around what are the priorities in front of us, and can we do that while we're still meeting our strategic objectives. So I'm not sure, did that answer your question?
Yeah. So there is some level of reevaluation along the way if something comes up.
Yeah, actually, let me stop sharing for a moment. I might have a good example of this.
And just doing a time check, we're about 9:30, so I think maybe
a
couple more questions and wrap it up.
Yeah, I'm going to share my screen one more time because I have something that might answer that question. Yeah, so again, you guys can look up the Curiosity. This is the Curiosity traverse map. In this area, we were originally planning on just driving straight across here, but the scientists had something high value up here that they wanted to go check out. So then we drove up there and did that. But yeah, we've made it all the way around here. We're basically heading up this canyon right now. So yeah, this is one of the mapping tools that you can look at and see where the rover is at. But I'll stop sharing there. It sounds like we are wrapping up for today. So thank you all for your great questions. It's good to see a lot of interest. I'll take a look at some of the chat transcript here, and like I said, maybe I'll try to put a little article together for the newsletter.
Great.
And answer some of those questions as well.
Thank you.
Evan, thank you for a great, fantastic talk.
You're welcome. I hope you all enjoyed it.
I'm glad you mentioned to us a while back that you'd be able to do a talk, and we happen to have the speaker that was hopefully going to be on this month couldn't make it, so we called on you. Thanks a million. Appreciate that.
Okay. Yep, it's my pleasure, Curtis.
Okay, thanks a million, guy. I appreciate it.
Mm-hmm.
Okay, the next thing we have on our agenda is the door prizes. Spencer and Alicia, it's yours.
Okay, so has everybody registered the door prize? Anybody not registered? All right. Let me set things up for 1 second. Alicia, you want to explain what's going on while I set this up?
Yeah, sure. Okay, so every journal meeting, we have an LS door prize where we give a series of gifts away on behalf of the club to the members. Today, we're going to be giving away Amazon gift cards, LAS hats, the one item from the LAS website of your choice, and laser and a red flashlight. So
okay, so I'm just pasting in the spreadsheet the names of the people who've registered, and then the first winner is so the spreadsheet picks names out at random. So the first one is Greg Thompson.
Hi, Greg. Yay.
Hey, how about that?
How about that?
We're
Wow.
not seeing your normal screen. Spence.
Yeah, we got a weird display. Yeah.
We only got
We're
a
seeing
date,
your date.
date timestamp.
What? Hang
We're seeing
on.
the date
We're
and
just
time,
seeing a
not your,
date and time.
not your
That's it.
spreadsheet.
You see it now?
Nope.
Nope.
Okay, hang on just a second. Let me.
Those drugs must be stay on.
Okay,
hanging in
how
there.
about that now?
There we go.
Okay,
There
all
we
right.
go.
All right, so
Hey,
what
Greg,
did
your
win?
hypnotism worked.
What did
Okay.
Greg win?
Yeah.
All right, I'm gonna delete Greg's name off the list, and next
We
one is
don't-
Carol.
We don't know what Greg won.
Oh,
Carol Crouch again?
Yes.
I win again.
Yes, you can't believe it.
Fixed.
Third month in a row.
Wow.
What'd she
Well,
get?
maybe we skipped a month last month. So what
What'd
you
you get,
win?
Alicia?
We cannot hear you, Alicia.
Gone. You won something,
Ali-
Carol.
Alicia is driving to Riverside, so
Yeah.
this might get interesting.
Oh, can you hear me now?
yeah, yeah.
Yes.
Yes, yes.
I was
So
like
what,
talking to a phone. Oh, God. Sorry.
what did Greg win?
Okay, so Greg won an Amazon gift card. Carol won an LAS hat.
That's it so far.
Okay.
No,
Joe.
Carol, excuse me. Carol, why don't you just go ahead and we'll donate the hat back. Carol doesn't want a hat. She doesn't wear hats.
Okay, so Joe Phipps was the next one.
Ooh, I won a hat.
Yeah, that's what you need, Joe, is a hat.
Yeah, Joe.
That's all right. I have no problem with that.
Okay, hold on. Let me
Okay.
write this down. Joe Phipps.
Hey,
Okay.
you were driving. How are you writing this down?
Yeah.
My mom was
Don't ask.
driving.
Don't ask.
Okay.
Home now.
So the next one
Nice.
is Andrea Scarlett.
Okay. Andrea Scarlett won a website item.
All right.
Yay.
Is she here?
I don't know.
Uh-oh.
Do you have to be present?
Not
Yes.
technically. Oh, but we've done this before where the person wasn't present.
Okay.
It's fine. They'll get a nice email prize. Okay.
Pablo.
Pablo won a red flashlight.
Nice.
Okay, let's see.
Oh, wow. Thank you. Appreciate it.
I can't read the name.
Okay.
No.
All right. So let's
Pablo
see.
Lewitt.
I'm trying to figure out how to spell the last name. Okay.
Okay. Marcus.
Lewett.
Okay. Thank you.
Lewin.
What? And Marcus.
Marcus. I'm sorry. I got ahead of myself. So Marcus and then Stefan.
You got way ahead of yourself, man.
Yep.
You're gonna make it so difficult on me. I'm
Think
like
these
sitting
peop-
there trying to figure out who won. Okay.
Marcus Rich.
Marcus Rich.
Okay.
What did he win?
He won an Amazon gift card.
And then Stefan Gorn.
Okay. Stefan Bourne won a LAS hat.
Okay.
Awesome. Yo. Thanks, Greg. Awesome.
Good. He's very happy.
They're nice hats.
Yeah.
Very nice hats.
Hang on just a second. Let me just take those names off of there.
Be very careful. I'm gonna write this down.
Okay. Okay. Not this one, but the next one after this one. Okay.
Oh,
All
Raphael.
right.
Diamond.
Okay. All right. Claude.
What? Whoa. There were a lot of people. Okay.
Yeah,
All right.
I had to delete two at the same time because that's screwed. I screwed up.
Okay. Claude won a website item.
All right.
Okay.
Yeah.
All right.
Now I can retire.
You already did.
How many more
You
do we
already
have?
did.
Two more.
Okay. Claire Schwartz.
Okay. Claire Schwartz won a red flashlight.
Okay.
All right.
And the last person is getting a laser. So.
Oh, here's the big one.
Chris.
Oh, go Chris.
Chris Velarde. Okay. Chris Velarde.
Yay!
Valdiva.
That's me.
Eva.
Got yourself a laser.
Yay! Thank you, guys.
All right, cool.
That'll complement the red flashlight.
Yep.
Okay, so I think we are done. Is there any other comments or questions somebody may have? If not, I think it's time to adjourn the meeting.
Okay.
We'll go ahead. Any other comments or questions or not? I will go ahead and adjourn the meeting.
Andy, did I
Nothing
answer
heard?
your questions?
Huh?
I was
What was
asking
that?
Andy if I answered the questions about the Mount Wilson Knights.
Annie?
Did I answer
You're
your
muted.
question?
Annie,
Did I
you're
answer your
muted.
questions about Mount Wilson?
Yes, it's September 4th.
Okay.
Thank you.
Thank you.
Okay, well, I'll go ahead and pound the meeting as adjourned. So the LAS August 2021 general meeting is officially adjourned at 9:41.